So, as you can hopefully see by the title page of the slideshow, we've got a new topic to start. So we finished the topic on electromagnetic induction, which was chapter 29 of the university physics book. So it's all basically based on what was in the university physics book. And the topic we're going to start today is based on chapter 30. And that chapter 30 is titled Inductance. I'd have perhaps called that chapter Inductors. So the chapter 29 on electromagnetic induction was looking at the general case of different types of induction, so induced magnetic fields and electric fields. And then this chapter 30 and the slides in this topic are based more on the technological applications of electromagnetic induction, which is basically inductors. So I'd have probably called that chapter Inductors, but anyway. There's also the survey that I sent a message about. So there's a link on Blackboard, and there was an announcement sent with the link as well about the survey that I set up for Fundamental C. So this was just to get an idea of what your thoughts are on the design of this module, because it's especially doing these lectures online, it's quite difficult to get an idea of how you guys are experiencing the delivery of this lecture. So I've got a survey, and we normally do this type of thing at the end of the module, but I wanted to do it sort of halfway through, just to help me get an idea of some changes I could make. I've had only one response so far. So it's basically saying the only thing was that the time spent on questions is a little long, so they suggested having a time limit. So, I mean, maybe we'll pick it up a bit when we do questions. Maybe go a bit quicker, but it's only just one response. So if you want to have your say on that or anything in this module, again, it's just one single open-ended question in the survey. So please just have a go at that then, if you got something to say about the module. Okay, so the learning outcomes for this topic is you'll learn how a time varying current in one coil can induce an electromagnetic force in a second coil that's unconnected to it. And you'll also learn how to relate the induced EMF in a circuit to the rate of change of current in that same circuit. So that's basically what an inductor does. You also learn how to calculate the energy stored in a magnetic field. And we'll also look at circuits that include both a resistor and an inductor, and learn how to analyze them. And we'll look at why electrical oscillations occur in circuits that have got inductors and capacitors in them. So you may or may not have heard of inductors, but they're all around you. So one example, well actually this is probably more in the United States, but when you drive up to traffic lights, a lot of them have an inductive sensor in the road that picks up whether the car is there or not. So actually I think most of the active sensors you get in this country are infrared, so it'll be like an infrared sensor on top of the traffic light to tell if there's a car there or not. But I think also in this country there's a few of these inductive sensors that you have at traffic lights. So there's just a large coil under the road that's got an alternating current in it, and then because the car is made of a conducting material, when it's near the car, you actually get electric currents induced in the car, and those in turn induce an EMF in that buried coil, which can be then picked up and used to determine whether there's a car there or not. So that's just one example of inductors. We'll come on to some of the others later on. So one important phenomenon that occurs when we've got two coils is mutual inductance. So if we've got two coils that are close to each other, so in this diagram we've just shown two sets of coils. So we've got coil 1 and coil 2, and they've just been kind of chopped in half, mostly so that you can see one coil, see both coils together. But these are just two complete coils that we're just showing the cross section of. So in mutual inductance, we can get an EMF, a voltage, electromagnetic force, in coil 2, and that's caused by a change in flux through it. So we already looked at this. So there's some flux going through coil 2 that we're going to call phi B2, and then any EMF that we get in coil 2 is caused by change in that flux. But if we have that flux being caused by current in another coil, so this isn't a permanent magnet or anything, then the only flux that we have going through that second coil is caused by current in coil 1. And so any change in flux in coil 2 is caused by a change in current in coil 1. And there's some proportionality constant for the current, the change in current in coil 1 and the EMF that we get in coil 2. So there'll be some EMF generated in coil 2 for that change in current. And we call this proportionality constant the mutual inductance, or M. So this is just basically saying how good of a mutual inductor this system is. So if these two coils were very far apart, then these wouldn't be very good mutual inductors. So we'd get very little EMF for a large change in current in coil 1. And that would mean we've got a low mutual inductance M. Whereas if this had been designed in such a way, so having these coils very close together, There's lots of different design parameters that you could change to make these better mutual inductors. But then if this was designed in such a way that we got a very good EMF, a very high EMF for a relatively low change in current in coil 1, then this would have a high mutual inductance. So we know that the EMF then in coil 2 is the negative of the number of turns in coil 2 multiplied by the rate of change of flux in coil 2. And then we're going to say that then this mutual inductance M, that's just this factor which relates the rate of change in current, so that the changing flux in coil 2 is caused by the change in current in coil 1. So it's just relating that change in current in coil 1 to the EMF in coil 2. It's just a factor there. And for a better mutual inductor, M will be bigger. So if we say a mutual inductor has got a very large M, it just means it's very good at mutual inductance and will get a high EMF induced in the second coil for a given rate of change of current in the first coil. So if you remember from the laws that we looked at in the previous section, so if we've got a current in a wire or in a coil, then the magnetic field that we get is directly proportional to that current. Right, so it just depends on the separation, the distance from that, and then the geometry. If you've got a coil there, then that changes it a bit, but we still have this direct proportionality. So we double the current, I1, then we double the magnetic field, B. And similarly, the flux that we get through coil 2 is directly proportional to the magnetic field. So that means that the flux through coil 2 is proportional to the current I1. Right, so they're always at a constant ratio. So we can re-express this equation. So we know that we've got a constant ratio between phi B2, the flux in coil 2, and current I1. So that'll always be the same. So we can just use the ratio of whatever current and flux that we have, and then it's going to get bigger. We'll get more mutual inductance for more turns, so we multiply by the number of turns N2 in coil 2, and then that gives us the mutual inductance and how good a mutual inductor we've got. So we can then go over this equation again that we just looked at. So we're saying that mutual inductance M. So we said that was equal to the number of turns in coil 2 times the flux that's going through coil 2 divided by the current in I1. But remember, this is mutual inductance, so the reverse happens. So if we send a current through coil 2, then we will induce an EMF in coil 1. So it just works backwards. And then the ratio of the number of turns in coil 1 and the flux through coil 1 divided by the current in coil 2 is exactly the same ratio as the first situation. So sending the changing current through either coil has the same mutual inductance. So you could use either situation to calculate the mutual inductance. And the units of mutual inductance is the Henry, named after Joseph Henry, who did a lot of work on inductors and inductance. And you can define it then as the flux in a second coil, whichever coil you want to call the second coil, per unit current in the first coil, which is then scaled by the number of turns in the second coil. Right, so we got more turns, we're going to get more EMF induced. So the units are the Henry, so we've got Henry, and that's, as you can tell from the equation we just looked at for mutual inductance, we've got number of turns, which is no units, and flux, which is Webers divided by current in amps. So 1 Henry is 1 Weber per amp. And then you can also express this in quite a lot of other SI units as well. It's 1 volt second per amp, which means it's also 1 ohm second, or 1 joule per amp squared. And like I said in a previous lecture, if you look down here on this slide, so these slides are on Blackboard. The only things that haven't got the answers to the questions in, but there's a link down here that links you to the University of Physics website, Masping Physics website, that's got a video example related to mutual inductance. So some other applications for mutual inductance is wireless phone chargers. So I haven't got one, but I think quite a lot of the more modern phones can have wireless charging on. So I can see how that would be useful. You wouldn't need to keep plugging and unplugging your phone. And these work on mutual inductance. So the base that you put your phone on, it's got a coil that's supplied with an alternating current, so it has to be alternating. So the current's going back and forth, and then that is generating an alternating magnetic force, magnetic field, and that induces an EMF in a coil that's in the phone. So you just need a small coil that's in the phone, and then that alternating magnetic field induces an alternating voltage in the phone, which can deliver energy and charge the battery up. So I think a more exciting application is in recharging electric cars. So, maybe in the future, all of us will be driving electric cars, and charging them could be a problem. And I think at the moment, there's a few experimental demonstrators of wireless charging for cars, and these basically the same. It's basically the same thing that is used for wireless charging of phones. Just obviously much bigger and more powerful because of you need way more energy to charge up an electric car. But these would be really useful if this technology can be worked out and it's deployed widely. Then all you need to do is park your electric car up to somewhere that's got an inductor under the parking space, and you can charge your car. So there's a lot of potential in this technology, I think. So another form of inductance is self-inductance. So mutual inductance needs 2 coils. So you've got a changing current in one coil inducing an EMF in a separate coil, but just a single coil displays the property of inductance. So in self-inductance, if we've got some coil in a circuit, then if the current in the circuit changes, then that causes a changing flux in the coil. So any steady current will cause a flux, and then if that current changes, we've got a changing flux, and we know that a changing flux through a conducting loop induces an EMF. The EMF actually goes the other way to the current, so it's actually pushing back against the current that is causing the EMF. And then we can define the self-inductance of a circuit. So we use the symbol L, other than the symbol M for mutual inductance. So this is just saying how good the self-inductor is. And similarly, we've got number of turns N multiplied by the flux that we get through the coil divided by the current. So again, flux and current are always proportional to each other, and that proportion will increase, so we'll get more flux for a given current depending on how good an inductor our inductor is. So larger value of L means you've got a better inductor, we've got more flux in the coil for a given current, and we've got more turns in it. Okay, so I've got a question then. So if you go to the Poll Everywhere site, so the pollev.com/Mark H, same site we always use. So here we've got a small circular ring of wire shown in blue, and this is inside a larger loop of wire that carries some current I. And then the small ring and the larger loop both lie in the same plane. And if I increases, the current that flows in the small ring is it's clockwise and is caused by self-inductance. B is counterclockwise and caused by self-inductance. C is clockwise, caused by mutual inductance. D counterclockwise is caused by mutual inductance, or E is 0. So I will activate, so I'll just activate the question on the Poll Everywhere site. So have a go at that. Okay, got 5 responses so far. Give that another minute or so. If you're not sure, just pick what Take your best guess. Okay, got 7 responses. Yeah. Okay, let's have a look at the answer to this one. So we've had one person go for B, it's counterclockwise and caused by self-inductance. 3 for C, it's clockwise and caused by mutual inductance. And 3 for D, it's counterclockwise and caused by mutual inductance. So what we're looking for is C, that this is it's going to be clockwise, this current, this induced current, and be caused by mutual inductance. Remember what we looked at. Mutual inductance is the induction of an EMF in one loop caused by the change in current in a separate loop, whereas self-inductance is the inductance inherent to just one loop. So we've got mutual inductance here. We've got an EMF, a current induced in one loop caused by the change in current in a separate loop. And then for the direction, we need to remember our right-hand rule from the last topic. So if you remember your right-hand rule, where it applies to both circulating current and the circulating magnetic field. So we can use our right-hand rule to determine the direction of the magnetic field induced in the large loop. So if we take our right hand, put our fingers in the direction that the current's flowing, and you can see we've got a magnetic field that's coming out of the screen, and it's increasing. Right? So we've got an increasing current, and the magnetic field is increasing then out of the screen. And if you remember our Lenz's law, which said that any induced effect will oppose whatever is causing that induction. So that means in the small ring, we need to induce a magnetic field that's pointing into the screen. So if you then take your right hand, flip it round, so your thumb's pointing into the screen, then your fingers will tell you which direction the current is going in that small ring. So if you point your fingers into the screen, you can see that your fingers are going round clockwise. So what we're looking for here is a clockwise induced current caused by mutual inductance. So another application of inductors is in electrical power distribution. So electrical power is sent down very high voltage wires. The there's not actually a huge amount of current going through them. They're just several thousand volts, so not much current actually needs to be sent down the main power carrying electrical cables. But these are subject to lightning strikes. So lightning strikes, again, very high voltage, so not delivering that much current, but that's still significant if the power transmission system isn't actually carrying much current itself. And then these effects can be minimized by using large inductors that are placed in the power transmission system. And like we said, an inductor tends to oppose any change in current to it. So the power transmission system should usually be delivering current at a steady rate. So the inductor wouldn't actually be doing anything. It wouldn't have any EMF in it. But then if we have, say, something like a lightning strike and we have a spike in current, then the inductor will tend to oppose that. So there'll be an EMF over the inductor that will push back against any current that is being sent through it. So it will tend to smooth out any spikes in current that you might have, say, caused by a lightning strike. So that's another application of inductors. So let's have a look in more detail at an inductor as a circuit element. So we've looked at circuits before. We've looked at circuits with batteries and resistors and capacitors, and we've looked at the symbols for them. So we've got the circuit symbol for a battery. This is the positive terminal. And we've got the circuit symbol for a resistor, which is usually this. Sometimes you might see it as a zigzag. And then there's the symbol for a capacitor. Just this, or sometimes this. If you've got an electrolytic capacitor that needs to have one polarity sent to it. But inductors are circuit elements themselves. So this is the symbol, the circuit symbol for an inductor. So if you see this in the circuit diagram, it means you've got an inductor there. And it would, if you looked at an inductor, it would basically look like the symbol, right? It's just a coil of wire. There might be a core to it, like a soft iron core that could better transmit or better carry the magnetic flux, but it's basically just a coil of wire. Obviously, bigger inductor would have bigger coil of wire, more turns in it. So if we think about a circuit then with an inductor in it, so we've got some connected to some box, so we can just vary the EMF in the circuit. Then the potential difference that we would measure over the inductor, so if we just put a voltmeter here, measured the voltage that we've got over the inductor, then that voltmeter is measuring EAB, which is just the difference in voltage at point A minus the difference in voltage at point B. And that voltage would always be, if we've got an ideal inductor here, so assuming there's no other components between A and B, it's just going to be the inductance of the inductor multiplied by the rate of change of current. So we're only going to see a voltage over the inductor when we've got some change in current through it. This is for an ideal inductor with no internal resistance. So an ideal inductor has no resistance associated with it. Obviously, a real inductor will have some resistance associated with it, in which case you just put another resistor in next to it to show what it's, to separate out its internal resistance. But an ideal inductor without any resistance in it, its voltage will always be its inductance times the rate of change of current. So we've looked before at resistors and the potential we would measure over a resistor. So if we did the same thing, took a voltmeter and measured the voltage over a resistor, then that voltage we would measure would be going through the resistor times the value of the resistance. And we looked at a water analogy for this. So we explained this in terms of flowing water, like a circuit with flowing water in it. So if we imagine that this current is actually flowing through a pipe with water in it, and then this resistor we can think of as just some kind of restriction in the flow. So if we've got a pipe that's got no restriction to the flow, and these are ideal wires that don't resist current, then when we get to a resistor, you can think of it as like a pinch point in that pipe where the pipe has been pinched off and it's now more difficult to push the water through it. Then the voltage we said was equivalent to the pressure. So if we just have a pressure gauge, then because we've pinched off the flow in a resistor, then we get a build-up of pressure on this side compared to this side. So we would measure a positive pressure on this side compared to this side. And then that's analogous to what we would see with a resistor in an electrical circuit. So if we measure the voltage across it, then that voltage would be equal to how much flow we've got multiplied by the magnitude of the resistance. So how much we've pinched off that flow in current. But crucially here, with a resistor, we will measure a voltage for a constant current. So if you've got a constant current I flowing through a resistor, then we'll measure a constant voltage through it, across it. Whereas for an inductor, so again this is an ideal inductor with no associated resistance in it, the potential difference across an inductor depends on the rate of change of current. So when you've got an inductor with constant current flowing through it, then the rate of change of current is 0. And then the voltage that we would measure across that inductor, so if we got a voltmeter and then measured the voltage here, if our current is constant, then our di dt is 0, and then no matter how big the inductance is, the voltage that we measure across that would be 0. But if we have an inductor with an increasing current, so again, the potential difference across an inductor depends on the rate of change of current. So if we've got an inductor where the current I is increasing, flowing from A to B, then we have a potential drop from A to B. So we've got a higher potential at A compared to B. So, like we said, the inductor will always tend to oppose the change that is applied to it. So if we increase the current this way, then the EMF, the voltage that we get across the inductor, will tend to oppose that. And I think I'm trying to think of a good analogy here. So I think it's also useful to apply our water analogy here to think about inductors. Although I think the analogy gets a little bit more abstract, but I think a good analogy for an inductor in a water circuit is a water wheel. So if we imagine like a kind of paddle wheel, try and draw that. So we've got some kind of paddle wheel that can turn. It's got some paddles on it. Then if this is in a water circuit, let's say we've got some pipes here. So if this is in a water circuit and we can flow water through it, then this water wheel is a good analogy, I think, for an inductor. So we've got the same properties here. So the rate of flow of water is analogous to the current that we've got in an electrical circuit, and any difference in pressure between 2 points is equivalent to the voltage. So if we started flowing water through this circuit, through a circuit, and pushing this water wheel around, and then we put some pressure meter here, so something that can measure difference in pressure between this point and this point, then if we say that this water wheel is ideal, so it doesn't dissipate any energy in it, so it's got no friction losses in it, so this makes it analogous to an ideal inductor. But then if we start to increase the flow of current, so increase the flow of water over this water wheel, it's going to take some energy and take some time to speed up. So initially, there's going to be higher pressure on this side compared to this side. Right, so that wheel will have some rotational inertia to it, so it will take some time to speed up. So if we send water flowing through our circuit this way, we'll build up pressure on this side initially while we're getting that water wheel up to speed. So we're going to oppose the flow of water that's trying to get that wheel started. So that's one analogy we can make for an inductor, or basically anything with some inertia to it, any physical or mechanical system with some inertia to it can make a good analogy for an electrical inductor. So we can also then look at what happens when the current is decreasing in an inductor. So if we've sent some current through an inductor, got it up to a steady state, so after we've left enough time for our current to flow through an inductor, then the EMF will drop to zero. So like our water wheel, we're eventually going to get it up to speed and it's not going to go any faster. So for an ideal water wheel, there'd be no difference in pressure between the two sides. And so for an electrical inductor, once we get to a steady current and there's no EMF over it. So again, the potential difference across the inductor depends on the rate of change of current. So if we are decreasing our current, then this di dt will be negative, will be less than zero. And so we have an EMF induced in our inductor, but it's going the other way than the situation where we've got increasing current. So again, this EMF is opposing the decrease in current that we've got. So the current is decreasing in this direction, and so we get higher potential on this side to oppose that decrease in current. And again, our water wheel analogy, I think works for that. So we think it's a water wheel, there's some paddles on it. And we put this in some kind of water circuit. It's got water flowing through it and turning this. So we've got this water wheel up to speed. We've sent some current through it, got it flowing, it's now turning. And so if we decrease the flow here, so if this flow gets smaller, then our water wheel is going to keep turning. So it's got some rotational inertia to it. It'll keep turning, and then even though we've decreased the flow here, it's going to keep pushing and trying to pump water this side. So we're going to have higher pressure over here. So if we had some pressure meter, we'd measure higher pressure on this side compared to this side, which is what we see in an electrical circuit. If we were to put a voltmeter there, we'd measure higher voltage on this side if we're decreasing the current through it. Okay, let's take 10 minutes break there. So I'll see you back here in 10 minutes. Okay, let's make a start. So we just looked at the situations where we've got increasing and decreasing current through an inductor. Let's have a go at a question then. So we've got an inductor here, and it's got some current I that's flowing through this inductor. Again, this is an ideal inductor, so it's got no resistance, got ideal wires with no resistance. If this current I is decreasing, then what do we have? Do we have the potential is greater at point A than B, potential is less at point A than B? The answer depends on the magnitude of the IDT compared to the magnitude of I. The answer depends on the value of the inductance L, or both C and D are correct. So activate that poll. Okay, so that's activated now. So have a go at that question on poll everywhere. Okay, you've got 4 responses so far. Okay, give that another minute or so. Not sure, just pick whatever your best guess is. Okay, let's have a look at the solution to this one then. So what we're looking for is A. So potentially it's greater at point A than point B. You had 4 people go for A, which is good, and 1 person went for E. So again, we did just look at this, so you could just remember, but I think it's better to have an intuitive understanding of what's going on here. So I think if you're dealing with this type of problem and you want to work out what the solution is, then again you can just remember that the inductor is going to oppose whatever change in current is going through it. So we've got our current here, and if that's decreasing, then we're going to have a higher potential at A to oppose that decrease. Maybe you might like to think of it as a water wheel analogy, so you can think of this as being like some little water wheel that we've got spinning. So if this gets wound up by the current, so it's pushing water in the direction that the current has got it started going, and then if this current then decreases, then this water wheel is going to keep spinning and build up a pressure here, pump water itself from its inertia and build up a pressure on this side, so it'll have a higher potential on A. So whichever way you want to try and imagine that. Okay, let's have a go at another question then. So here we've just got some statements then. So from what we've talked about, conductors, so this is ideal inductors with no resistance associated with them, then which of these statements about ideal inductors is correct? So is it A, when it is connected in a circuit, an inductor always resists having current flow through it? Is it B, inductors store energy by building up charge? Is it C, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is reduced to 0 in one time constant? So D, an inductor always resists any change in the current through it? Or E, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is 0 after a very long time? So have a think about that, and I'll activate the poll everywhere side question. Okay, so that poll's activated now. Okay, you got 4 responses. Excellent. Again, if you're not sure, it's more important that you respond to these polls. Another minute or so. Okay. Right, let's finish there. So, 6 responses. Everyone went for D, which is what we're looking for. So if we go through these, we say statement A, so when an inductor is connected in a circuit, an inductor always resists, so then current flow through it. You know, that's not true, because when the current is steady, so there's no change in current, then the resistance of an ideal inductor is 0. So no, that's not true. Inductors store energy by building up charge, so they don't build up any charge. It's a magnetic field that they build up magnetic flux. So it's capacitors that build up charge. It's not B. When an inductor and a resistor are connected in series with a DC battery, the current in the circuit is reduced to 0 after one time constant. So we'll come on to later what happens over time, but it's certainly not going to go to 0. So it's actually one time constant will take you to 1 over E if you switched off the current, that is. It's C. And then E, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is 0 after a very long time. So again, that's not true. If we connect up a battery, we know that we'll reach some steady state of current, and then that current will be dictated by the resistance. So the inductor is just what it takes to get to the current that's dictated by whatever resistance. So no, it's not E. Okay, so we looked at some of the differences between resistors and inductors. So a resistor is a device which dissipates energy, and it can't be recovered from the electrical circuit itself. So any energy that is lost in the resistor, well, that'll basically just heat it up. So the resistor will just get hotter as more energy is dissipated in it. And then we know the energy that's dissipated in it. We know the power from power dissipated in it will be IV. So there'll be some particular voltage across our resistor and some particular current flowing through it. And then the energy will be, the power times the time. And then that will be lost in the circuit. So that will just go as heat, which will be lost, and there's no way of getting that back in a normal electrical circuit. By contrast, in an inductor, this is actually storing energy, and this can be recovered from in the circuit. So as we increase our current to some steady rate, some energy will go in, so we'll have some voltage over our inductor as we're increasing the current. So we've got some IV, some current times voltage there. So it's not as simple. It's not, because we've got changing voltage and changing currents, and we'll come on to later how we get the energy stored in there. But then once that energy goes into the inductor, once we switch off the current, then, or reduce it, then this inductor will oppose that and try and send more current through. So it will then dissipate energy back into the electrical circuit. It's not necessarily 100% efficient, so that energy that goes in, no system is 100% efficient. So there will be some losses in there, but actually inductors are pretty good at storing energy. They're usually quite efficient. So most of that energy that's stored in an inductor can then go back into an electrical circuit. So that energy is stored in the magnetic field. So when we have an inductor in a circuit, then it generates a magnetic field inside the inductor, and it's that magnetic field where the energy is actually stored. So if you want to work out what energy is stored in an inductor, then if we remember that the voltage over an inductor is equal to the inductance L multiplied by the rate of change of current. So at any particular instant of time, the power supplied, P, will be the voltage across the inductor at any instant. So that voltage will be changing, but at any particular instant, we've got particular voltage over the inductor multiplied by the current going through it. So then the power then is going to be the inductance times the current times the rate of change of current. Because we know that the voltage is L di dt. So then the energy du supplied to an inductor during some time interval dt, so over some tiny slice of time that we'll call dt, we've got some tiny piece of energy that's going to be supplied to the inductor. So that energy du will be the power, wherever the power is, times the time. So the energy is power times time. So we've just got this tiny slice of time dt, and the power, because it's just some tiny slice of time, then the power will be constant over that tiny slice of time, even though over time the power is changing that's supplied to it. So we know that the power is Li di by dt. So if we multiply that by dt, then du, the little tiny bit of energy, is equal to the inductance I times whatever the current is multiplied by whatever tiny change in current we've got over that time. So if we then integrate this to get the total energy that's stored in an inductor, so we're going to do the integration as a function of I. So we can take this inductance L out of the equation for the integration, and then we're going to integrate the current from 0 up to a final current, which we'll call big I. And so if we take an integral of that, then that's going to be half Li squared. So the energy stored in an inductor is half Li squared. Okay, let's have a go at a question then. So a steady current flows through an inductor. If the current is doubled while the inductance remains constant, the amount of energy stored in the inductor increases by a factor of √2, B increases by a factor of 2, C increases by a factor of 4, D increases by a factor that depends on the geometry of the inductor, or E, none of the above. So have a go at that. I've just activated the poll everywhere site. Okay, got 4 responses. For another minute or so. Okay, so just had some more responses in. Okay, we had 6 responses. Right, let's have a look. Okay, so deactivate that question. So we had one person go for A, increases by a factor of √2. 2 for B, increases by a factor of 2, and 3 for C, increases by a factor of 4. So what we're looking for here is C increased by a factor of 4. So if you remember the energy, E or U, if you like, it's equal to half L I squared. So if the current is doubled, then we're going to increase the energy stored in the inductor by a factor of 4. Okay, let's have a look at circuits that have a resistor and an inductor in them. So any real inductor, any circuit with a real inductor in it, will have a resistor and inductor in a circuit. So any actual inductor will have some resistance associated with it. So it's some coil of wire. It's usually quite relatively thin wire. It's got some length to it, so there'll be some resistance associated with it. We can also put it in a real circuit with an actual resistor in there. So an RL circuit contains a resistor, an inductor, and we'd usually have some EMF source in there, something that can supply voltage, like a battery. So this shows some typical RL circuit. We've also got some switches in there. So if we close switch 1 and then connect our inductor and resistor combination in series with our voltage source, then we can supply some current to the inductor and store some energy in it. And if we've got another branch of this circuit with another switch in it, 2, then once we've built up some current to a steady state in our inductor, then we could open switch 1 and close switch 2 and then dissipate any energy that's stored in it. And if we could then measure the current or the voltage in here, so we could put a voltmeter or a current meter in this circuit to measure what's happening and connect that to an oscilloscope and look what's happening over time. And then we could look at the temporal characteristics of this type of circuit and see how the current and voltage changes over time. So if we were to take our circuit and then at some initial time, so we'll say at t equals 0, then we're going to close our switch S1 and look what happens to the current. So say we've got some ammeter in the circuit, and then that could be connected to an oscilloscope, which could then track what happens to that current over time. And so we're going to start at time equals 0, and the current can't change suddenly from 0 to some final value, because the EMF induced in the inductor opposes that current. So it has to start from 0 and then rise to some particular value. So it will start increasing at a high rate to start with. And as the current increases, the rate of increase of the current becomes smaller and smaller and eventually tends to some steady value. So this current that it would reach would be simply the EMF supplied by the voltage source divided by the resistance in the circuit. So again, our inductor, I'm going to say is ideal, and we could lump any actual resistance that is in the inductor in the resistance in series with the inductor in the circuit. So what we see here, we've got some particular pattern of change, and this is actually an exponential. So it's an exponential decay, but an exponential decay to a steady value. So typical normal exponential decay. So if we've got some time and some value, whatever it is we're looking at, an exponential decay look like this. The growth we have in an inductor is just this flip around. So this is just going to be whatever value we get here. Just call that V times 1 minus the exponential decay. So that's e to the minus t over tau. So this exponential decay, the equation for that would be V equals e to the minus t over tau, where t is the time and tau is a time constant. So that time constant tau is just how long it takes for the value to decrease by a factor of 1 over e. So once this is 1 over e as its start value, then that time constant is tau. For the increase in current, it's going to be 1 minus e to the minus t over tau. So it's just doing this and rising to a steady value rather than decaying to 0. But the same applies. Right, so it's going to, after a time constant of tau, then the value of the current that we have would be the start current, the steady state current I multiplied by 1 minus 1 over e. So let's look in more detail then about how we get this particular response in current as a function of time. So if we think about our circuit that's got an EMF source and a resistance and an inductor, then we can apply our Kirchhoff's loop rule. So we know we've got a loop here in this circuit, and then we know from Kirchhoff's law that if we go around this loop, then all the EMFs in that loop, all the voltages in that loop must equal 0. So if we were to go around this way, so go around anti-clockwise, then here we're stepping up in voltage for our battery, so that's going to be some positive value. And for the resistor, then we're stepping down, so that's going to be a negative voltage, and then the voltage over the resistor is IR. And then for the inductor, again, it's going to have positive bias here at we're starting at time equals 0, and then we know then that will give a negative voltage, and then the size of that voltage will be L di dt. And then adding all of those voltages together, we know equals 0. So if we rearrange this equation so that we get di by dt, so the rate of change of current, then that's going to be the EMF minus IR over L, the inductance. So again, rearranging that a bit, we get epsilon over L equals R over Li. Now we just want to get the R and the L on its own, because we want to know how the resistance and the inductance, what those two together do to affect the shape of, or the form of this temporal response. So let's then pull out a factor that gives us just R over L. So we need to pull out the I from here, and then if we do then minus epsilon over R, then that will mean we can just get R over L on its own. And then we can bring this dt over this side and this I minus epsilon over R to this side, so we get di over I minus epsilon over R equals R over L dt. So we've now got the R over L on one side, resistance divided by the inductance. And now we can integrate this function. So we'll just change over the variables a bit. So we'll just call the I dashed, so the instantaneous current I dashed, and then the time, the instantaneous time, t, we'll call that t dashed, just so we can use I and t for the limits on our integral. So the final values of I and t. So we can then integrate like this. So we've got our integral between 0 and I, and that's going to be equal to negative the integral of R over L dt. So we can then integrate this integral and evaluate it. So for this side, do the integral, evaluate between 0 and I. This side, integrate and evaluate between 0 and t. So here we've got, on the left-hand side, we've got a function, so it's basically a 1 over I minus epsilon over R. So when we're integrating a 1 over reciprocal function, then that gives us natural log. So we've got the natural log of I minus epsilon over R. And then when we evaluate this between I and 0, then we're going to have the natural log of I minus epsilon over R minus, so if we do this, evaluate the integral, we're going to have then minus natural log and I is 0, so that will just be minus epsilon over R. And then from our rules of how logs work, then that will be log I minus epsilon over R over minus epsilon over R. And then integrating the right-hand side, we just have R over L times T. And we want to get rid of this natural log, so we can take exponentials of both sides. So we take an exponential of a natural log, we'll just get rid of it. So that just leaves us with this part, and then take the exponential of this part, we've got e to the power of minus r over L times t. Right. Then we can just multiply both sides by minus epsilon over r to get rid of this part on the bottom, and then we can subtract. Then we can add epsilon over r, so that gives us a function relating the current that we see to the time, which is what we want to know. So if we just rearrange this slightly, then we come up with our final expression, which describes how the current changes with time. So this is saying the current I is E over R, which is our final value, multiplied by 1 minus e to the minus r over L times t. So r over L is our factor here. Typically, though, with exponentials, the form of an exponential is you have e to the minus t over tau. So tau is the life, the time constant. So the time taken to get an increase or a decay by a factor of 1 over e. So here this r over L is multiplying by t. So if we have this expressed as a time constant tau, then we just need to flip it round. So if we are dividing t by that r over L, then it becomes L over r for our time constant. So that means then our time constant for our circuit, so the time taken to get a change in current by a factor of e, which is the way exponential decay and increase works, and how it's described, then the time constant is L over R. So for a circuit with an inductor and a resistor in it, then that time constant gets bigger for larger values of the inductor, and then it gets smaller for larger values of resistance R. So if we want a large time constant, so if we want a slow change in current, then we want a big inductor and a small resistor. Okay, let's finish there then. I'll hang on for a few minutes if there's any other questions, but other than that, I'll see you next week. Oh, one thing, I just forgot to mention something important. So there's now a Mastering Physics homework available on the Mastering Physics website for what we did in the last topic on chapter 29 on electromagnetic induction. I'll send out an announcement as well, but that's now open on the Mastering Physics website. So if you go into the Mastering Physics website, you should see a homework titled FPC, Fundamentals of Physics C, electromagnetic induction. So that should be available from today. And I think there's two weeks to complete that homework. So please have a look at the Mastering Physics website. And on that, I'll see you next week.